So good morning everyone. Today we will continue with the signal operations. In our last class we have been discussing about this time shifting, time scaling and time inversion. Now today we will be discussing about the combined operations. Okay. Now this combined operations, it basically involves a combination of all these three operations. So as you can see, all the three operations are carried out simultaneously. So that is x of at minus b. At minus b, this component, it would discuss about the what you call this delaying or advancing, whereas at, this a component, it talks about this this scaling factor, and the magnitude of a, it also discusses about the time inversion. Okay, so this can be achieved by two methods. Out of these two methods, I prefer the first one, okay, over the second one, this one. So in the first one, what happens, the xt is time shifted by b, so we get x of t minus b, and then we perform time scaling by a to obtain x of at minus b. Okay, first we perform the time shifting and then we perform the time scaling. Okay, in the second method, what it is done, it is just the reverse. First we have to do the time scaling by a to obtain at, and then we have to do the time shifting by b by a of the signal at. Okay, so this gives us x of at minus b. Why? Because we replace t with t minus b by a, and then if you do it, you get x of a of t minus b by a, which gives you x of at minus b. Okay, so if you see the next one, it is a bit complicated because you have to use a fraction to do the operation. So however, it's up to you whether you want to perform it in by the first method or the second method. It's totally up to you. Both of them, it would give you the same result. Okay, now if a is negative, as I already told you, if a is negative, time scaling, it involves time inversion. Okay, so let us take some example. So say we are having a what you call signal fn, which is given by 1 3 5 4 2 3 2 1 3. Okay, and these are all the n values written. So minus 4, minus 3, minus 2, minus 1, 0, 1 2 3 4. Okay, so these are the time instances. Say for example, we have to get a signal f of minus 2n minus 2. Okay, so what should be the first step? The first step should be to determine the delay. Okay, if you see, so we have to do the time shifting first to get x of t minus b, and then we will be performing the time scaling. Okay, so herein, so what is the delay fraction? We are having fn. If you have to do the time shifting, here the time shifting is delay by a unit of 2, so we will get f of n minus 2. Okay, so f of n minus 2, in our last class we have already discussed, if it is a delay, we will move this pivot to the left hand side. So see, how many units? By 2 units. So the pivot is moved to the 2 units, and this is our f of n minus 2. Okay, now comes f of 2n minus 2. Now this scaling factor it is coming. Now when we are doing the scaling factor, if it is a negative 2, so negative means, as I told you, it is involving time inversion. So before going for the time inversion, we will just go for the scaling. So in the scaling we have f of 2n minus 2. So 2n minus 2, what we talked about, if it is being multiplied by 2, then every alternate numbers have to be striked off. Okay, so the origin, it comes just like this, then 1 2, 2, 3. Okay. Now what? Now if you get f of minus of 2n minus 2, that means there is a time inversion, so it will just flip. So this 3 comes here, 2, 2, 5, 1. Okay, you get my point? Now the next thing is that if we want to do want to get f of 2n plus 2, so plus 2 means this pivot will move to the right hand side. See, the pivot has moved to the right hand side. Okay, then f of 2n plus 2, again we have to strike off from the center the alternate numbers, so we have striken off, and this is the signal 2n plus 2. Now suppose if it would have been 0.5 n plus 2, that means the signal length would be increased, and see, after every value, say 1, then next value we have interlaced with 0, then 3 interlaced with 0, 5 interlaced with then 0, 4 interlaced with 0, then 2 interlaced with 0, 3 interlaced with 0, 2 t was at the origin, so it would remain at the origin, again it would be interlaced with 0, then 1, 0, and then 3. Okay, so I hope all of you have understood how we can do these signal operations if you are given with any kind of signal. Okay, now coming to the next topic, basic continuous time signals. So there are 4 basic signals: unit step function, unit impulse function, complex exponential signals, and sinusoidal signals. Okay, so unit step function, if you see, for unit step function it is regarded with u of t, and it is having value from 0 to infinity, a value of an amplitude of 1. Okay, so we can delay it by t0, so it becomes u of t minus t0, 1 for t values greater than t0. Okay, when we are shifting it. Then unit impulse value, so delta t equals to 0 at t not equal to 0 and infinity at t equals to 0, but the integral of delta t from minus infinity to infinity, which comes out to be, because we are considering it to be very small quantum, epsilon, so this epsilon, if you do the integration, so within that region the integral value, it comes out to be 1, and we use this value to do the sampling. Okay, so again we have the unit impulse function, where we can see we are having a signal at t equals to 0, and then we can shift this to t0. Then sampling property, we have previously discussed this. So if you are having ft multiplied by delta t, and say if this a over here, if the a is 0, then what you would get is that ft delta t. So what it says is that, say xt multiplied by delta 0, it would be x of 0. So ft multiplied by delta t minus a, which is equal to fa delta t. So we will be getting the value at fa. Okay, so these are the proof, we need not discuss this over here. Then shifting, I already told you, if we shift say xt multiplied by delta t minus alpha, then we will be getting the value of x of alpha, whatever the value of x at time equals to t equals to alpha, we will get that amplitude value. So complex exponential they are given by this equation, xt equals to e to the power j omega naught t. So if we break it down, it comes out to be cos of omega naught t plus j sin omega naught t. Okay, and this has got a periodicity of t equals to t0 equals to 2 pi by omega naught. Okay, so these are complex exponential because we are having this j component, the complex number, into the equation. So if so, from where we are getting this? So we are getting this because we are having xt equals to e to the power st. So which we can break it down into e to the power sigma plus j omega t, which is equal to e to the power sigma t multiplied by cos omega t plus j sin omega t. Okay. Now, if s is equal to only a real number, then what you means? This factor, it is equal to 1. Okay, when this is 1, then we get real exponential signals. Okay, we get real exponential signal. Now sinusoidal signals, we all know these sine waves and the cosine waves, they are the sinusoidal signals, and they are represented in this form: x equals to a cos of omega naught t plus theta. This theta is nothing but your phase angle in radians. Okay, and the fundamental frequency, it is given by f0 equals to 1 by t0. Okay, so this is a continuous time sinusoidal signal. Similarly, we have basic discrete time signals. So first one is the unit step sequence, unit impulse sequence, the same things, complex exponential sequences and sinusoidal sequences. So unit step signals, see, from n equals to 0 to infinity, we will be having amplitude values of 1. Again, if it is being delayed, so delayed by how many units? Delayed by k units of time. So it would be shifted to the left hand side, right hand side, sorry. Then unit impulse, again an amplitude of 1 at n equals to 0. Again, if we delay it, it would look something like this. Then complex exponential signals, again the similar thing over here. And then periodicity we have already discussed in one of our lectures. So when capital N, it is a real number, then we say that it is periodic in nature. Then general complex exponential signals, xn equal to c alpha n, where c and alpha are in general complex numbers. Okay, so in some cases it might so happen that c is equal to 1, which is becoming this thing, and alpha it may be e to the power j omega naught. Okay, then real exponential signals, if c and alpha both are real, then these exponential signals, it becomes the real exponential sequence. Sinusoidal sequence, again we have this thing, so from there we get the sinusoidal sequences. Okay, now coming to the next topic over here, systems. So what are systems? Systems are mathematical models. Systems are mathematical models. Okay, say for example, I hope every one of you have studied about a non-inverting amplifier. Okay, in your analog class, analog electronics class in your BTech, in the first year usually they teach it, first year or in the third semester. Okay, so what is the I will take that example to make you understand what are these. So what are this y, what are this t, which is basically the transfer function, and what is the x. Okay, so what you have basically in the equation for the non-inverting amplifier, it is V0 equals to 1 plus R2 by R1 into V in. Now what is V0? V0 is nothing but y. What is this? This is say A, which is regarded as the gain, and what is Vi? It is x. Okay, now if you compare this equation with this equation, what we have? Capital T, it is equal to A. Okay, so what is capital T? Just now I told you that it is a transfer function. What is a transfer function? It is nothing but a mathematical model. Okay, so it is just the input output relationship. So what we consider is that when we are giving a signal x to a particular system, it is getting amplified by this transfer function. Okay, now what may happen over here is that the transfer what I have told you, it is just a linear thing. Okay, it may vary with time or vary with frequency, not time, frequency. Okay, so if it varies with frequency, then it becomes filters. Okay, so to keep our things simpler, we will just consider uh, the gain, and we will not consider that the frequency is being changed. Okay, so as I told you, if you are having this kind of thing, so where you are getting an output and it is being scaled by t when you are giving an input x, and this mathematical operator, it is called the transfer function of the system. Now a system, it can have a single input and single output, and it may be regarded as SISO system, single input single output system. Similarly, there might be some cases where you may have multiple inputs and multiple output. They are called MIMO system, multiple input multiple output system. And there might be some systems where you have multiple input and single output. Okay, it is also possible. So these are some of the classes of the systems. Okay, now what are the example over here? You may have seen the MIMO systems. You have in the hospital, you may have seen these bedside monitors where they have sensors for, say, ECG signal processing. Then they may have sensors for respiratory signal. They may have signal for the what you call oxygen level, oxygen level saturation sensor, it may have. Then fourth one, it may be the BP sensor. Okay, so many sensors may be there. And what would be your output? The ECG, it may show you the direct ECG, or it may also show you the, after processing, it may show you the heart rate. Okay, then respiration rate you can get, RR. Then PO2 output you will get, BP output you will get. Okay, so this is a classical bedside monitor. It is a classical example of multiple input multiple output system. Now coming to the classification of the systems, the systems, they are broadly classified into these categories: continuous time and discrete time systems. Second is systems with memory and without memory. Then causal and non-causal systems. Then linear systems and non-linear systems. Then time invariant and time varying systems. Linear time invariant system, stable systems, and feedback systems. Okay, now when we talk about the biomedical systems, or the systems which are generally used for biomedical devices, they follow the causality. That means they are causal signal, because when we are attaching the sensor and we are starting it, then only it starts processing the signal. What has happened in the past when you have not put the sensor, it has no record of that. Okay, so when you have given the input, from that input onwards, it will do the processing, and hence they are called causal system. Then linear systems. What are linear systems? Linear systems means, as I told you, that on a frequency wide there may be some differences. Okay, however, if you forget the frequency, suppose if I am giving a signal, a system, say 2 volt of signal, and it is having a gain of 2, then my output would always be 4. Okay, as the time progresses, it should not either increase to 5 or 6 or 7, or it should not decrease to, say, 3 or 2 or 1. right? So if our system follows this thing, there are certain rules, we will look into this, but on a broader topic, whatever the input you are giving, whatever the scaling factor, it remains the same for the total period. Then these type of systems, they are regarded as linear systems. Okay, and if this gain factor it varies with time, then it becomes the non-linear systems. And adaptive systems, adaptive filters you must have heard of. So where there is a continuous change in the gain, so as to we get a particular output. Okay, so those systems, they are in general not studied in the classical biomedical signal processing. Okay, so those systems, they are regarded as non-linear systems. Okay, then time invariant. With time, this scaling factor should not change. Okay, so using these three, especially the second and the third system, there is a category of systems which are regarded as linear time invariant system. Linear time invariant system. Okay, so linear time invariant systems, they should follow the linear systems, they should follow the linearity and time invariance properties, and then they are called the linear time invariant systems. And if they are causal in nature, then we can say that for the classical signal processing techniques, this system, it is suitable for biomedical signal processing. So if I give you a question that find out whether this system it is suitable for biomedical signal processing or not, then you have to check for the causality, you have to check for the linearity, you have to check for the time invariance. Okay, then continuous time and discrete time systems, the systems which take input as the continuous signals and also generates output as the continuous time these signals, then those systems are regarded as continuous time systems. If they take an input of discrete time and also give an output of discrete time signals, then they are regarded as discrete time systems. Then comes the systems with memory and without memory. So what are these? So if you have a register, you are giving some signal and you are getting some output, so that should be instantaneous. Whereas if you look into the capacitive systems, where you are taking the time consideration from minus infinity to t, so it is taking all the informations of the input from the past instances. Memoryless, it is taking the present instance signal component and instantaneously it is generating the output. It is not considering the past input or output to generate the current output. Okay, क्या हुआ? But yeah, सोच रहे हो कुछ? खोए हुए लग रहे हो? Anyway, so in the memory system, what you have in the memory system, it will consider either the past inputs or the past outputs to generate the present input. Then these systems, they are said to be having the memory. Then causal and non-causal. So how do you check? So over here you have to draw the time scale. So say n, 1, 2, 3, 4 and so on, minus 1, minus 2, minus 3, minus 4 and so on. So this is the origin. At 0 we have the origin. Okay, anything on the left on the 0, these are the past values. On the right side, these are the future values. Okay, so if I ask you with respect to minus 1, n equals to minus 1, which will be the past values? So minus 2, minus 3, minus 4, they will be the past values. Okay, and 0, 1, 2, 3, 4, they will be the the future values. Now suppose I give you this example, yn equals to x of n plus 1. So what you have to do? If you see, when y equals to 0, for 0th instance, what we will get? We will need values which are appearing in the future. Okay, so x ka input which is in future, if we get that value, then only we will be getting this thing. So futuristic value non-causal. Okay, so this would be non-causal. Similarly, you have to perform this with negative and positive values. So say y of 1, it would be x of 2, and y of say minus 1, it would be x of 0. Okay, now take the second example, y of n equals to x of minus n. So y of 0 equals to x of 0. This is a causal system. Then y of 1 x of minus 1, it would also say that it is causal, but stop, because you may be tempted to say that this is a causal system, but we have to look into the negative half also. Say y of minus 1, then what it happens? X of 1. Here it gets non-causal. If in any of these cases, if the system becomes non-causal, then the system is regarded as non-causal system. Okay, the system is regarded as non-causal system. Similarly, this is the thing what I have again tried to make you understand over here, the same thing. Now coming to the linear systems, we will stick with the example of the inverting amplifier having a gain equals to 2. So what it says, given that t of x1 equals to y1, t of x2 equals to y2. Say for example, x1 equals to 1. What should be our output? Output should be 2. In the next instance, say x2 equals to 2. What is our output? 4. Now what it says, if we perform x1 plus x2, which is equals to 3, okay, what should be our output? It should be 6. Okay, so x1 plus x2, when we give it, so it is 3, and we get the output of 6. Okay, so this is what it is told over here. Now if you see the output over here, if we add y1 plus y2, y1 plus y2, it is equals to 6. Okay, now we need to see this thing. When we are independently giving x1 and x2 signal, whatever is the output, whether that output of those single instances x1 plus x2, and when we give a combination of the x1 plus x2 as the input and the output of this one, whether they are same or not. If they are same, then it is said to follow the additivity rule. Then it is said to follow the additivity rule. Now in the next example, homogeneity or the scaling property. In the homogeneity and the scaling property, what happens over here is that, again let us consider this one. So we are having x1 equals to 1, we have got 2. Now what happens if we perform 2 of x1, we get 2, and the output should be 4. Now we have scaled it by a factor of 2, Now whether the output, when we have not scaled the thing and then we have used the scaling factor, and if you multiply y1 multiplied by 2 and whether it is equal to, so say if it is x1 dash, so whether this is equal to the output of the second instance where we have put x1 where we have given the input as the x1 dash. Okay, so again over here what is y1 dash? Y1 dash is also 4. If you multiply it over here, it is 4. Y1 multiplied by 2, it is 4. Again this is the y1 dash, so y1 dash is equal to 2 into y1. Okay, so in both the cases again if you see the output remains the same, right? So this is called the scaling property. If it is following the scaling property, then also it is regarded as the linear system. So in other words, what you can say, if you are scaling the system by a units, your output should also be scaled by a units. Okay, so this is the another property which the linear system should follow. So first one is the additivity, second one is the homogeneity. Okay, when we combine these two properties, we call it superposition property, wherein we talk about, initially we have talked about x1 x2, second we have talked about ax. Over here if you see, it combines both the systems a1 x1 plus a2 x2. Okay, which is equal to, it should give you a1 y1 plus a2 y2. So if you see, compare this equation with the previously mentioned two equations, then it is a combination of these two, and when we go for the combination of these two, we get the superposition property, which is basically a combination of the additive property and the scaling or the homogeneity property. Okay, so these are some of the examples. I will discuss one of the examples over here. Yt equals to t multiplied by x of t. Okay, so find out whether this system is a linear system or a non-linear system. So for x1 input we get y1. So what is y1? Y1 is t into x1 t. I have not put, but let me put it over here, x1 t. Okay, for y2, because we are changing the input, so for x2 we get y2, which is equal to t into x2 t. Okay, now what we have to do? We have to perform this thing, y1 plus y2. y1 plus y2 is t of x1 t plus t of x2 t, and we get t of x1 plus x2. Okay, in the next scenario, y double dash, so here what we have done, it is basically y1 plus y2. Y dash is equal to y1 plus y2. In the next step, we have to change the signal x1t plus x2t, and we have to replace this fraction over here. So when we are replacing this fraction over here, y double dash, it is equal to t multiplied by x1 plus x2. So our c and d both are equal. So this is a linear system. Okay, again let us take this example to, you will be having a clear idea. Yt equals to x square t. Okay, let us put it as x square. Okay, so for x1 we will be getting x1 square, for x2 we will be getting x square 2, for y dash t we will be getting y1 plus y2, we have to put it, so we get x1 square plus x2 square. However, when we are changing this signal, so y double dash t, it is becomes x1 plus x2 whole square. Okay, x1 plus x2 whole square. So our c and d, they are not matching, so it is a non-linear system. Similarly, you can do for the other stuffs also, where we can find it is both of these other systems 3 and 4, they are linear systems, okay, because y dash is equal to y double dash, here also y dash equals to y double dash. Now coming to the time invariant system, so as I told you that a system is called time invariant if a time shift, delay or advance in the input signal, it causes the same time shift in the output signal, okay. So when we delay the signal by tau units, our output should always also be delayed, okay. Suppose we have delayed the signal by 2 units, our output should also be delayed by 2 units, okay. Now how to do this? So suppose you are having the signal yt equals to t into xt, okay. Now first what we have to do is that we have to delay the signal. We have to delay the signal. And how do we delay the signal? Y of t comma k, it is equal to t of x of t minus k. We have delayed the signal. In the second step, we will replace the t value with t minus k, okay. Wherever we will find t, we will be replacing it t minus k. So we get this t, it gets t minus k, x of t minus k, okay. So 1 and 2, they are not equal, and since they are not equal, this system, it is a time variant system. Similarly, in the next case, y of t comma k, we get the signal has been delayed x of t minus k, but ut, it is not a signal. Ut, we use it, it is a step function and it is not an input signal. It is a step function, okay. It is a, so it is not a signal. Since it is not a signal, this will not be delayed, okay. However, in the second step, when we go and we replace t with t minus k, over here t minus k is also t is also replaced with the t minus k. Again here 1 and 2, they are not equal, so this is again a time variant system. Similarly, in the next one, y of t is equal to x of t square. So in the first case, x of t square minus k. In the second thing, we are replacing t, so this becomes t minus k whole square, okay. This is again a time variant signal. Now please look into these two systems, okay. They are similar, but if you see, one is time invariant and another is time variant. Over here we have x square t. When we delay the input signal, it becomes x square t minus k. Again, when you change, because it is basically, if you can also write it as xt whole square, right. Now when you are replacing the t with t minus k, you are getting again x of t minus k, okay. However, if there would have been another t over here, then it would have become time variant, because it is not there and we are getting 1 and 2 as equal, hence it is regarded as time invariant system. So linear time invariant systems, if they follow the linearity, if they follow the time invariant property, then they are regarded as the linear time invariant systems. Then stability of the system. Stability of the system, it is given by bounded input, bounded output stable systems. So in this, suppose we are having a system, if we given bounded input, that means which can be quantifiable or measured, and if we get an output y0 which can also be measured and calculated or measured, then it is regarded as bounded input, bounded output. Say for example, if I give an infinite amplitude signal, then automatically the system will also generate a y value which is having an amplitude of infinity. So then it becomes unstable. So the criteria is, if we give a bounded input, our output should also be bounded. Okay, we will see that when we discuss the filters. So what do you mean by bounded? Bounded means, suppose you have given an impulse signal, that means at t equals to 0 you have given an impulse. So over time its signal should decay to amplitude tending to 0. At t tending to infinity, your amplitude should be tending to 0. If it remains constant, just like your say ut step function, then it is called marginally stable. And if the output it increases continuously to infinity, then it is called unstable. Okay, so because you have given a bounded input, and under this condition you have got the bounded output, the system would be regarded as bounded input, bounded output. Okay, and systems. Then feedback systems, any system which is taking the past input and the past outputs into consideration to calculate the present input, those systems, they are regarded as the feedback system. Okay, with this we complete this chapter. From the next class we will start with transforms. Okay, do you have any questions? No? Time invariant. Tell me what you didn't understand. We are given with the equation yt equals to t multiplied by x of t. What is the input over here? Input is this signal. We have to delay this signal. So in the first step, y of t comma k is equal to t. We are delaying the signal. Okay, so x of delaying means we have shown t minus k. So this k is the delaying factor. In the second one, y of t minus k. So wherever we will find t, it will be replaced with t minus k. Okay, so y of t minus k, it is equal to t minus k multiplied by x of t minus k. In the first case we are delaying the signal. Okay, we are delaying the signal. In the second case, wherever you find t, you replace with t minus k, or in case if I give you as n discrete signal, you replace it with n. Process remains the same. Okay, anything else? Now it is clear. If you look over here, in the first case, u of t was not changed because it is not the input. Input is x of t. Only this was changed and this was not changed due to that reason. Whereas in the second case, both were changed because t was replaced with t minus k. Okay. Anyone else?